Exam 2 is on Friday. And its topics up through I word this differently every time, but up through
stresses of objects loaded like stresses.
Yes, that's a good way to word it, yes. Stresses on objects loaded like stress elements. Yeah. You know me. You get me.
I wrote it down word for word.
Yeah, I said it perfectly last time. So who's going to be the one to come in to the test on Friday and then say, like, I didn't know we were supposed to do stresses on objects loaded like stress elements, and I spent all my time preparing for internal loads. Somebody, probably Kenny. Yeah, okay, you volunteer. Okay. All right. So before I go on to the new stuff, I'd be happy to answer questions related to the test. Anybody have any questions? Here we go, like you're looking for one?
No, I'm going to pull up all the questions that I have, right?
Okay.
Can you do number 5 for the 24th?
Yeah.
In February?
Number 5.
Or is that a test question?
Yes, that could be a test question. So you have an object like this, and you're given a distributed load on the top and bottom of 8,000 newtons per meter squared. And you're also told that there's a uniform distributed load that comes to a max to a total force of 5,000 newtons, equal and opposite like that. And we're told that the cross-sectional area is 0.01 meters squared. We want to calculate the stress tensor. We want to talk about, okay. So I said that this was a distributed, I said this 5,000 was a distributed load. But actually we're assuming that those are point forces. And so the next question is, where on the body do we trust our results? And then what's the stress tensor with maximum shear? Okay, so if we're using a coordinate system like this, then the y normal stress is just equal to negative 8,000 newtons per meter squared, so pascals. Why is it negative? because it's in compression. Like if you just imagine this, whatever shape it is, just imagine turns into a stress element, you know, and you just have to adjust the values. And then the only other non-zero value would be the XX stress. Would that be positive or negative? Positive because it's in tension. And so the value is going to be 5,000 divided by 0.01. So that is 500,000 pascals. And so the stress tensor is, well, let's see, 5 times 10 to the 5, 0, 0, 0, negative 8 times 10 to the 3, and then zeros. And where do we trust the values? And what are, that's right. Since these are point forces, in order to be able to calculate these stresses, we have to assume that they're uniform distributed loads. But since we're replacing the actual load with a different version of that load, we have to throw out any information that we have about this region near the end on both sides. So we trust all the stuff in between the red, but not in the two red regions because of St. Venant's principle, yep. And then the maximum shear stress is the maximum principal stress. Okay, well, first we need to calculate the principal stress tensor from this stress tensor. Done. So anytime you have a stress tensor that only has normal stresses, then that's already a principal stress, and you can skip that step. Imagine how discouraging it would be, especially if your calculator didn't do it, to go by hand and calculate the principal stresses and get these values back. And so maximum principal stress minus minimum principal stress divided by 2 is pretty close to just half of 5E5, but what do you get for that? 2.54. Is that what it is? 2.54 times 10 to the 5 pascals. And if you needed a stress tensor for that instead of just a value for the maximum shear stress, what axis would you rotate 45 degrees around? About the z-axis, because you want to take the axis corresponding to the middle principal. Any questions about that one? Any other problems you'd like to see? Okay. All right, so okay, I know what that's supposed to mean. So back to internal loads. Up until now, this is true of statics and deform up until now. We've always assumed that weight acted as a point force at the center of mass of the object. But that's not really what weight does. It doesn't do a calculation of the centroid and then apply a force there. It applies a little bit of force everywhere. And so really it's a uniform distributed load. And when you're doing internal load calculations, that's an important distinction. So we have to understand when it's okay to take this distributed load that represents the weight and represent it as a point force. So up until now, weight has been treated as a point force at the center of mass. But really, it's a uniform distributed load. And in internal load calculations, if you treat it as a point force, you get wrong answers. Exclamation point. So, how do you know when it's okay to treat this distributed load as a point force and when isn't it? That's a pretty that's a pretty narrow reading. So when is it okay to treat weight as a point force? Because even in these internal loads calculations, we're going to at some point have to treat it as a point force to do the calculations. That's why we did it before, because we couldn't do the calculations with weight as a distributed load. Okay, so you can treat weight as a point force once you've chosen the body to isolate, but not before. Okay, so here's the rule. You can treat a distributed load, not just weight, but any distributed load, as a point force once you've chosen the body to isolate. Not before. So let me do an example with weight. And I'll show how this works. So let's say we have a cantilever that's not allowed to rotate about the z-axis. And let's say that it has a mass of 100 kilograms and a length of 2 meters. But it could still be rotating with a constant angular velocity then. What are the internal in the beam? Okay, so the first thing that we do is calculate the external loads. In this case, they're not going to come up since we're working from the left. But here's what a free body diagram would look like. So that weight, instead of treating it like it's concentrated at a point in the middle, it's really a distributed load. And the value of that distributed load is just the total force of 981 divided by the length. And so this distributed load is 490.5 newtons per meter.
Does this work only for the homogeneous bodies basically made out of the same material, or is it always works for any type?
You're right. It would be different if it had chunks that were different materials.
Okay.
You'd have to do it chunk by chunk.
What if it's an ununiform shape?
You'd have to do it piece by piece. Hopefully not, but I guess I'd have to see the example. Hopefully you can calculate it. All right, so we're ready to start doing the internal loads calculations. How many places are there where the subfunctions could change? 2, just here and here. So how many cuts are we going to do? 1. Right. So cut 1 is valid for all x's from 0 to 2. Thanks. That was weird. Okay, so we're skipping all this part with these loads over here. And we're just dealing with this part. The distributed load is 490.5 newtons per meter. And the only other loads on the piece that we're looking at are the internal loads: tension, shear force, bending moment, and torque. There's not going to be any torque in this one, but I'll keep writing that in there. And now we've chosen, and this distance is x. We've chosen the body to isolate. So now we can represent the weight, that distributed load, as a point force. So I'm going to redraw the free body diagram with the weight represented as a point force, and you're going to, well, hopefully you'll see, maybe you won't see yet. So we have those internal loads, T, V, M, and torque. And now we want to represent that weight on this piece as a point force. Well, the weight on the whole thing was given initially, right? The weight on the whole thing is 981, but we're not looking at the whole thing. We've chosen this small piece that only has a length of x, so only some fraction of the weight is acting on this. And furthermore, if we treated the total weight as a point force, it would be acting 1 meter from the end, right in the midpoint of the whole thing. Okay? But the weight that's acting on our isolated piece isn't acting at the midpoint of the whole thing. It's acting at the midpoint of what we've isolated. Okay? And so let's see. What do you get if you have a distributed load of 490.5 newtons per meter, and it's acting over X meters of this.
490.5x.
That's right. So acting right at the midpoint, you have a point force of 490.5x. And it's acting at the midpoint, so what's this distance from the end?
X over 2.
X over 2, yep. And so Newton's second law says 0, negative 490.5x plus p 0 and 0 negative v, I'll just combine those two vectors into one, is equal to 0. And so that tells us that p is equal to 0 the whole way. But v now, this is the first time we've seen this. Is it? No, we saw it also with the triangular loads. V is equal to negative 490.5x. And then go to the moment equation. For z. And remember, our about point is at the left end. The moment arm for this 490.5x is x over 2. The force is 490.5x. Would that be a positive or negative rotation about that red point on the left? Negative, clockwise. And then you have plus m minus vx is equal to 0. So m is equal to positive 245.25 x squared plus vx. Vx is equal to 490.5 x squared. So we get 245.25 x squared minus 490.5 x squared. So our final function for m is equal to negative 245.25 x squared.
In our free body diagrams, when we do the cuts and include just like 490.5x, do we also have to draw the external torque, even though if it doesn't exist there?
No, you can leave that off if it isn't relevant for. So yeah, I had forgotten about that, but yeah, to be complete about this, we should do the sum of the torques around the x-axis, and you just get that torque is equal to 0. So if there's a problem with no torque around the x-axis, you can leave it off if you want. Okay, so let's see what happens. So this was the right way. What?
When you say the right way, are you talking about going from the left to the right?
That's not what I'm talking about.
The correct way.
The proper, correct way, in the sense that I'm going to show now what happens if you treat that weight as a point force from the start. Okay? And we'll see the answers are different, and hopefully this will kind of clarify what it means to treat the distributed load as a point force before you've chosen your body to isolate. Okay? And I'm going to do this in red because I can. Yeah, red means stop. Treat the distributed load as a point force. Don't do it this way. Someone else is going to do this on the test and be like, I did it just like your example in class. The one in red that said, don't do it this way.
What if they're going to do it in red?
What?
What if they're going to do it
Do it in red.
Looking
Yeah.
wrong.
You just need to listen to my words on this and not do it this way. But I think this helps clarify it. So I'm going to. Okay, so free body diagram of the whole thing. You have the weight down of 981. And you have these reactions. Okay, so how many places are there in this problem where the sum function can change? 3 in this case if we're treating this as a point force. 1, 2, 3. So we're going to do 2 cuts. Cut 1 is for x between 0 and 1. That's right. So there's the internal loads. But that weight force is over here somewhere. Right? Follow what I mean? I can't read you guys. Okay. So Newton's second law says T negative V is equal to 0. So T is 0, V is 0. The moment equation says M minus Vx is equal to 0. So M is equal to 0. That's false. This is the right, because what's really happening is gravity is pulling a little bit on all of these pieces. But before we chose this body to isolate, we had already decided that we were going to treat weight as a point force acting outside of that body. You know what I mean? That was the horrible mistake that you made on this problem. Okay? Yes, I assume that you thought this was the right way to go. But, okay, so that's the key distinction. So you get that wacky stuff. Now we'll go to cut 2. X is valid between 1 and 2. So this time the weight is acting there, where this distance is a fixed 1 meter. And you have the internal loads. Newton's second law says T minus V plus 0, negative 981 is equal to 0. So T is equal to 0. V is equal to positive 981. Thank you. And then the moment equation says we have a moment arm of 1 and a force of 981. Is that positive or negative? Negative. And then plus M minus Vx equal to 0. So M is equal to 981 plus Vx, which is 981 minus 981x. Yes. Right. These are. Okay, so this is wrong because we represented the distributed load as a point force before we chose the body to isolate. One other thing to notice about these problems. Anyone have any questions about that?
I got a question about
Yeah.
like V in general. And this one will work. How you wrote like V is a down arrow, but it's a negative number.
Where?
So you have V equals negative 981. It's
Uh-huh.
a down arrow. So that would be
Uh-huh.
in the positive direction. It would be like up, right?
That's right. That's right. So yeah, think of it, this is a way to think about that so you'll never get confused, because it's easy to get confused. I mean, everyone gets confused about this sometimes, but if you get confused, remind yourself to think about it this way and you'll never be confused again, okay? What this always says is it's a variable that's a number times a unit vector, okay? The unit vector is the direction of the arrow, and the number, the variable is a number. So this unit vector is 0, -1, you know. That V comes out to be negative. So if you multiply negative 981 times 0, -1, you get a vector that's 0, positive 981.
The x-axis torsion,
Yep.
when it's right, do you just mean 0, 0, 1 as the unit vector? Or wait, is that the right way? That's not the right way of thinking of it. No,
Yes. When you draw with those torques, when you draw this, that is a okay. So this vector is this torque.
So just convention, right is positive, left is negative.
It's axis directions. Although,
Just in terms of how we draw the arrows.
for internal loads, you mean?
Yeah.
For internal loads, the convention is like this. If you're working off the right end, that's positive. If you're working off the left end, that's positive. But when you're summing the moments, like in one of the laws of motion, you're using vector directions. So
I mean, if you have on the left side, if you have 500
Mhm.
to the left, when you write that value, will you write negative 500 or positive 500?
like if you're using,
If you have it on the left, you have to have it on the right, right?
okay, so if you have,
Okay, no,
okay,
I got it. But
all right.
They're both going the same way.
This and this? No, they're equal and opposite, like the fons.
So one will be positive and one will be negative.
When you put them in Newton's laws, this one would be called negative, and this one would be called positive. But when you're when you're drawing it for internal loads, these would both be called positive values of t. Even though this would be a vector of negative t, 0, 0, and this would be a vector of positive t, 0, 0.
And then the right-hand rule works on those if we're looking at it like
Yeah,
from the top.
that's right. So a torque this direction means a rotation like that.
And then that would be counterclockwise. And then for that one, you would look at it from the same spot, right? And it would be the opposite
It would be
direction.
a rotation this way.
So you would look at it like that, not like this. Isn't it this?
You can look at it the same way.
Then it would still be positive, counterclockwise.
No, I mean, you're just looking. Oh, I see. Like whether you're looking that direction or
Yeah,
that
if you draw
direction.
your eye and the guy
Yeah.
looking at it, you'd want them both from the same side, right?
Yeah, this whole conversation is getting into a murky.
Because now that we kind of, well, we don't understand it, but
Yes, we did.
always are going from the left anyway.
Yeah, so let's always go from the left, anyways. Yeah.
To the right.
So there are two things at play in all these internal loads calculations. There is the direction that you define to be a positive variable value, and that's the weird one. You know, that's this and this and this and this, okay? So that tells you what you're calling a positive variable in all these cases. But then, and we're not used to that. That's a new thing. But then there's also the component side, the directions of the components when you go into Newton's laws. And those, you take this weird stuff and put it back into the directions that, so now to use these in Newton's laws, this tension T would be in the positive x. This tension T, that vector would be negative T0. This V would be 0, negative V. This V would be 0, positive V. This M would be positive. This M would be negative. This T would be positive, and this T would be negative. Yep.
So if you have like a negative value on the left side for the moment about the C axis,
Mm-hmm.
the right side would you represent that like as a positive or as a negative too? Like the way you have it now. I mean that doesn't matter the sign. It's always
I always draw it the same way and just let the sign tell you whether it's so. If you draw a moment like this M here, and then that M value is equal to negative 100, that means the same thing as positive 100 with that rotation going the other way. So I would just keep that rotation drawn like that and just let the sign tell the story. Okay, so I think a lot of this stuff, the way to clear this up is just to do more example problems. Okay, so let's do that. I think, ooh, yeah, quiz. Let's do the quiz. Okay, so we'll do that next time.
I mean,